Hello everyone, this is our next lecture in our Material and Energy Balance class, and today we're going to be in sections 8.1 and 7.5. We're just going to look really briefly at 8.1. Most of the material is going to come from 7.5, but I'm using section 8.1 as a preview for the rest of this course and what we're going to cover. So that is in pages 403 to 411, and then we're going to move on to section 7.5, which is pages 367 to 372. Go ahead and read that up first and then follow along with this video. What we have done in the past few lectures is derive the energy balance for an open system and a closed system. And in the process, we came across this idea of specific enthalpy and specific internal energy. So far, every example that we have done, the values of these specific energies have been given to us in the question. And where we are going for the remainder of this course is really looking at the tools that we have to find or estimate these values of specific enthalpy or specific internal energy. So specific enthalpy and specific internal energy are called state properties, and what this means is that they only depend on the state of the species. State of the species means at what temperature and pressure and what phase they are in. And it really doesn't depend on how it got to that state. So what do I mean by that? So for example, in this case, I have a plot of P versus T, pressure versus temperature. And we have this gas that goes from state 1 at temperature T1, P1, and H1, so a state of state 1, to state 2 where it becomes a temperature of T2, P2, and H2. When we say that specific enthalpy and specific internal energy are state properties, what we mean that is, as long as it gets from state 1 to state 2, it does not matter how we got there. The specific values of the energy will be the same. So I could go take path A by increasing pressure and temperature concurrently. I could take path B where I first increase pressure at a constant temperature, and then once I get to the correct pressure, I now hold the pressure and I increase the temperature to T2. I could do the opposite and go path C, or I can just be really fun and just do a weird little loop and get path D, but I'm still going from state 1 to state 2. The change in the enthalpy that we are looking for is essentially the final state minus the initial state, so it's H2 minus H1. And because these are state properties, it does not matter whether we take path A, B, C, or D. If we do the calculations for all of these paths, the change in the enthalpy is going to be the same. So why does this matter? This is because sometimes we are not able to find the final and the initial state very easily, so we need to create hypothetical paths, and in doing so, we are able to calculate the change in the specific enthalpies. Let's look at this example, and this is from section 8.1. For example, let's say we want to change in specific enthalpy for phenol, a solid phenol at 25 degrees C to 1 atmosphere, and we want to get it to vapor phenol at 300 degrees C and 3 atmospheres, and we want to find what is the change in specific enthalpy due to this change. So we have a phase change, we have temperature change, and we have a pressure change. If we were to draw it out, what we really want is getting from solid to vapor from 25 degrees C, 300 degrees C, and 1 atmosphere to 3 atmospheres. In general, you're not going to be able to find values for the final state minus the initial state. If we do, that's great. You can find the specific enthalpy, the change in the specific enthalpy of this true path directly. But, like I said, in general for phenol, which is not a very common compound to have, we're probably not going to be able to find a table for that. So what we need to do to calculate our change in enthalpy is to create a hypothetical path, and along each path, all we're doing is changing one thing. We're either changing the phase, changing the temperature, or changing the pressure. So for example, in this case, we're going to first change the temperature by heating it up to 42.5 degrees C, keeping it as a solid, keeping the pressure at 1 atmosphere. So it's just a simple heating process. And why do I go to this weird temperature of 42.5 degrees C? That turns out to be the melting temperature of our phenol. At 1 atmosphere, that's our normal melting temperature. So once we get there, all we can do now is just change the phase. So we have a latent heat of melting. We are at this melting temperature and pressure. We are changing the phase, and that gives us our latent heat. The next step, we can heat it up again further to get to our boiling point of phenol. This 181.4, that's our boiling point of phenol at 1 atmosphere. And now we can change it to the vapor phase by simply vaporizing it. And that is our latent heat of vaporization at that temperature and pressure. Now we are almost home free. We have 2 more steps to go. We need to bring it up to 300 degrees C and 3 atmospheres. So let's do it in 2 separate steps. we're going to heat it up again to 300 degrees C and then compress it by increasing the pressure to 3 atmospheres. So in this way, we are going to learn different methods of calculating each of these steps. We can calculate our overall change in enthalpy, this delta H true, by just the summation of all of these paths. Because, like I said, specific enthalpy is really a state property. It doesn't matter how we get there. By doing so, we are able to actually estimate this true enthalpy change. So what we do need to find, just based on this loop itself, we have 3 different processes where it's just simple heating. Delta H1, delta H2, and delta H3, we're just increasing the temperature, but we're holding the pressure constant. In delta H4, we are changing the pressure but holding temperature constant. And lastly, we have our latent heats of melting and latent heat of vaporization. So for the remainder of this class, we're going to look at the different tools that we have to calculate all of these different values. The first tool we're going to have are tables of values, and these are the easiest. If you can find a table to use, always just use that. All you're doing is looking up the final state, looking up the initial state, take one minus the other, and then you are done. So for example, if you have a table for phenol, spanning all the different states across a whole bunch of different temperatures, a whole bunch of different pressures, all you need to do is to look up the enthalpy for phenol, vapor phenol, 300 degrees C, 3 atmospheres, subtract that with solid phenol, 25 degrees C, 1 atmospheres, and then we are done. If you don't have that, we're going to go to what we call thermodynamic correlations, where we are going to use some equations to calculate or estimate what happens, how does enthalpy change if we change temperature or we change pressure. And lastly, we're going to cover psychrometric charts. This is not simply just for looking up specific enthalpies, but this is specific for air-water systems, so they are humidity charts, and from there we can look up more than just enthalpies, but we'll use the enthalpy values in our material balance questions. So for the rest of this class, what we're going to do is looking up tables of values, and the most common values that you're going to find are that for water, because water is such a common compound in this world. People have done a whole lot of experiments ranging a whole bunch of different temperatures and pressures and tabulated all the enthalpy values. So today you're going to get a lot of bang for your buck in that we are going to cover 5 different tables in our textbook. So open up your textbook and follow along in these tables. We're going to cover table B5 all the way to table B9. What are these tables? Tables B5 and B6 are for water, and they are specifically for saturated liquid and saturated steam. So they are right on the vapor-liquid equilibrium line when you think about the water phase diagram. Tables B5 and B6 are essentially tabulating the same values. The only difference is that B5 is arranged by temperature and B6 is arranged by pressure. So depending on which variable you are given, one of the tables might be easier to read than the other. Table B7 is also for water, but in this case it is superheated steam or subcooled liquid, so we are not necessarily just on the vapor-liquid equilibrium line. We can be in the superheated region or the subcooled region for the liquid. And lastly, just very briefly, I'm going to talk about table B8 and B9, which are for other compounds. These are not going to be very useful, but I just want to point out that they do exist. All right, so let's go through each one of these tables slowly. We're going to do tables B5 first. Tables B5 and B6, like I said, they are really the same. One is arranged by temperature, one is arranged by pressure. If you look at the phase diagram, tables B5 and B6 are giving values for states that are along the vapor-liquid equilibrium line. The first thing to note is, what is that reference state that's picked for these tables of values? We'll find where that is by looking up the values where our enthalpy or internal energy is 0. And if you look up table B5, you'll see that the enthalpy and internal energy are 0 for a liquid phase, 0.01 degrees C and 0.00611 bar. And this turns out to be the triple point of water. So this is the reference state that was used to generate all these values in these 2 tables. The reference state being the triple point of water. All right, let's delve further deeper into this table to try to help us understand what these values are. So here I've taken a small section of this table so we can look at it together. Let's look at what happens at temperature of 40 degrees C. So that's the first line in this small table down here. We see that at temperature equals to 40 degrees C, we are given one single pressure, and that is 0.0738 bar. Remember that we are along the vapor-liquid equilibrium line. That means at a specific temperature, we have already set the pressure. And what is that pressure? That pressure is the saturated vapor pressure or the pure component vapor pressure, P star, that we have learned earlier in one of the earlier chapters. So this is essentially P star at 40 degrees C. Where can we double check this value? We have been looking up P star values in table B3. So if you look that up, you can see there's 55.324 millimeters of mercury. Convert it to kilopascals, and you'll see that it is indeed consistent with this table, and we get 7.38 kilopascals. All right, let's look at the three different variables that's given here. We have the specific volume, we have the specific internal energy, and the specific enthalpy. So I picked out all the values they give you for both water and for steam. So you can either have saturated liquid or saturated steam. Those are the different values. And let's take a look at the trends that we see. What are the differences between these values in the liquid phase and in the vapor phase? The first thing you can do is to just double check your math. We know that the definition of enthalpy is internal energy plus P times V. So we have all the values. Take the U hat plus the pressure that's given, so 7.38 kilopascals multiplied by the V hat, and verify that you end up with H hat. You can check the math for yourself there. The next thing you will notice is let's compare the values between our specific volume, and you will see that the specific volume for a liquid is much, much smaller than that for a vapor. This should make sense to you. What is specific volume? Is the volume occupied by 1 kilogram of water. On the left-hand side, you have 1 kilogram of liquid water. On the vapor side, you have 1 kilogram of steam. And we know that the volume occupied by a gas is much, much higher than the volume occupied by a liquid, and that's why you see those values, or the difference in the values as seen in this table. The next thing you'll notice is that the energy values, the specific internal energy and the specific enthalpy, the values are higher, much higher for the vapor phase than in the liquid phase. Again, this should make sense to you. The energy of the molecules in a vapor phase are much higher. They have higher energy than that in the liquid phase. And so what you want to do is you can also double check these values from table B6. Well, I've taken this from table B5 at 40 degrees C, but we know that this is at 0.0738 bar. So flip over to table B6, look up pressure of 0.0738 bar, and double check that you will end up with a temperature of 40 degrees C, and double check all the enthalpy values, internal energy values, and the specific volume values to make sure that you can understand how to read these two tables. So we have one more column we haven't looked at, which is this middle column that says evaporation, right, under the H hat between the water and the steam. What this is, this H hat evaporation is essentially the latent heat of vaporization. So now I'm going to take a different temperature at 100 degrees C because that is our normal boiling point of water at 1 atmosphere. And you can see from this table, the latent heat of vaporization is 2257 kilojoules per kilogram. We can also think about this latent heat from the definition of latent heat, which is just the enthalpy in the vapor phase minus the enthalpy in the liquid phase. Where do we get those two values? It's just simply to the left and to the right of this evaporation value. So we have our 2676 for steam and our 419.1, and you can verify that if I take one subtracting the other, you end up with the latent heat of vaporization. The other source of latent heat of vaporization that we can look up is in table B1, and table B1 gives the latent heat of vaporization at the normal boiling point, which is at 1 atmosphere. So from table B1, you can flip open to that, look up water. The latent heat of vaporization at 100 degrees C, in this case, is given in kilojoules per mole. So we have 40.656 kilojoules per mole. Let's convert it to kilojoules per kilogram using our molecular weight of water. So it's 18 kilograms per 1,000 mole. And you end up with the same value, or at least close to that, 2259 kilojoules per kilogram. So all this is just to verify that different sources should give you roughly the same value for latent heats and enthalpies. All right, so now that's for table B5 and B6. Let's move on to table B7. B7 is for superheated steam or subcooled liquid water. And to visualize this in terms of the phase diagram, the values that are given in that table is the values that are within that red box, or the states that are within that red box. You're varying from a pressure of 0 bar all the way up to a 1,000 bar, and a temperature from 50 degrees C to 750 degrees C. We are no longer constrained along the vapor-liquid equilibrium line, so we have either the superheated vapor region or the subcooled liquid region as well. In terms of the reference state, it's not explicitly stated. You can't find a zero value within this table, but if you read the text, it turns out that the reference state is the same, triple point of water, which means that you can use table B5, B6, and B7 concurrently. You can take values from table B5 and use it with table B7 because they all have the same reference state for water. We have a region of values in a box. So if you look at page 650, which is the first page of table B7, there's a region that is boxed up. And what this box is indicating is that is the region for water, or liquid water. And what you see within that box, they can tell you that it's liquid water, is that it has lower energy values, lower specific enthalpies, lower specific internal energies, and it also has a lower specific volume. So we saw why this is so from the previous slide between liquid and vapor. So let's look at a single row of values. At any pressure that we have, we are going to be in the superheated vapor region. So we are going to be right here. So let's assume that for any P, we're going to be at some temperature T, and we can pick the temperature that we want. You will see that in that table of values, you have the P value and then you have a T set value right below that. That is the saturation temperature. So what it's giving you is that at that pressure, even though we are not at that temperature, what we can do is we can move leftwards and give us our saturation temperature right there. So you don't have to go back to table B5 and B6. You can actually get it from this table itself. And in addition to that, we can actually get all the enthalpy values associated with the saturation temperature and pressure right there. We're going to move left horizontally to get the properties of that from columns 2 and 3. So let's look at the example right here. In this case, I picked temperature of 350 degrees C and 80 bar, and I have the table up right here. In terms of the enthalpy at this state of 350 degrees C and 80 bar, we can see that the enthalpy value is right here, 2990 kilojoules per kilogram. So that's what we are talking about, for example, if we are right here. We're in the superheated region. So what happens if we want the saturated properties? So what happens if we want the properties right here? We just go leftwards all the way, and you can see right below the 80 bar, you have the saturation temperature of 295 degrees C. And in the first two columns, you'll see saturated water, saturated steam. You can look up those values, 1317.1, 2759.9, and those are your enthalpy values for saturated liquid and saturated vapor. So we can double check this because we know that these values should be consistent with table B5 and B6, which gives only saturated values. So please go ahead and double check, verify with table B6 with a pressure of 80 bar. So look up a pressure of 80 bar and double check that you will end up with a temperature of 295 degrees C, and you can get these enthalpy values as well. So we can also calculate the degrees of superheat. This is just a review of what that means. A degree of superheat is the temperature minus the saturation temperature. So in this case, we're at 350 degrees C. It only requires 295 degrees C to be saturated, so our degrees of superheat is 55 degrees C. So that's table B7. And lastly, I'm just going to introduce table B8 and B9 really quickly. They are just giving a whole bunch of other compounds. You will look at, and based on the caption, you'll see that the reference state is P equals to 1 atmosphere and T equals to 25 degrees C. And these are all vapor phase compounds. So in that table, B8 and B9, you will see a column for water as well. This is water vapor. It has a different reference state. So it's P 1 atmosphere, 25 degrees C, vapor. Different reference state from tables B5, 6, and 7, which is the triple point of water. Which means you cannot use these tables, you cannot cross-use these tables. You cannot pick a value of water from table B5 and then use something from table B8 or 9 because they are defined from a different reference state. You will see that there's a limited range of temperatures. It's only for a single pressure, very limited number of compounds, and so in general this is not very useful. Occasionally you might find something given the question or given your application that might be able to use these tables. But otherwise in general, for most of the other compounds, we're going to look at thermodynamic correlations, which is the next lecture, and we'll cover that next. So that's all we have for this lecture. There will be a video example related to how we're going to read these tables and getting more practice to read these tables and putting it into our energy balances. Work hard, be smart. I'll see you next time.